Dr. Sharma with the conservation of momentum principle. Okay. So, have you ever seen a car crash in slow motion? Have you seen? So, two vehicles slam into each other, crumple, then move as one mangle unit, right? But have you wondered how fast does that wreck move after the collision? Can you predict it? Think about this. These questions actually unlock one of the most powerful tool in physics. Okay, the law of conservation of momentum. Okay, let's dive in. First of all, what is momentum? We discussed about momentum in my previous lecture. So the momentum is a measure of motion that combine the mass and velocity. That is, in mathematically, product of the mass and velocity is the momentum. Okay, so that means the bigger or the faster the something is, the more momentum it has. That's why stopping a truck is harder than stopping a bicycle, because truck has so much mass. But bullet is so small, but its momentum is so high. Mass is so small, but its speed is so high. So that means momentum is so high for the bullet. Law of conservation of momentum says if you have an isolated system, you have a closed system where no external forces like friction or air drag are acting, the total momentum stay constant. That means momentum before collision, event means interaction, right? The momentum before collision must be equal to momentum after collision. Okay, so total initial momentum must be equal to the total final momentum, isn't it? If you have two objects, let me write down here. Suppose object 1 with the mass m1 and object m2 with, it has a velocity, initial velocity is v1i. Okay, object 1's velocity initial, and object 2 has the initial velocity v2i. After some time they collide, m1 will move in this direction, sorry, one velocity of the part, the mass 1 with velocity v1f, and m2 will go in the same direction. So m2 will go in this direction with the velocity v2f. So if this is the closed system, no other external forces are acting, then the momentum before collision must be equal to the momentum after collision. So momentum before collision, that means the momentum of the mass m1, initial momentum, that is b1 m1 b1i plus m2 b2i, that is the initial momentum before collision. Now what is the final momentum after collision? That is equal to the m1 b1f plus m2 b2f. This is the conservation of momentum principle. Okay, that means the momentum lost by one object during the collision must be exactly same amount is gained by the another object, because the nature keeps the momentum perfectly balanced like a cosmic accountant. Okay, the nature is the cosmic accountant. Okay, we have a CA and other accountant to do our financial things, but nature is a kind of the cosmic accountant. It try to balance everything. Okay, well, you have example, a 1000 kilogram car, suppose say that is car A, moving at 12 meter per second speed, then it hits another 1200 kilograms car, let's say car B, that is at rest. After the crash they stick together. What is their final velocity? How do you find that one? So you can use the same situation here. So the before collision and after collision. Let's solve this problem. Okay, so the before collision, so before collision, so the car A, it has the mass, let's say m1, it has the 1000 kilogram. What else? So its initial velocity is v1i, which is 12 meter per second, and car B whose mass is still 1200 kilogram. I am sorry, its mass is little higher than that. So, its velocity initially is 0 because it is at rest. So, the after collision what happens? Let me talk about after collision. Okay, they stick together, that means kind of inelastic collision. Okay, inelastic collision. So, that means their velocity, final velocity of the car 1 and the final velocity of the car 2 must be the same. Let us say that is the final velocity Vf, because they stick and they go with the same velocity. So, conservation of momentum principle, let me write down here. So, the initial momentum before collision and the momentum after collision. So, momentum before collision, momentum of the first car m1 v1I plus m2 v2I is equal to m1 v1f plus m2 v2f. So, this is 0 because initially the second car has the 0 velocity. So, that means m1 v1I is equal to m1, both have the same velocity vf, m2 it has also same velocity vf. So, the vf is equal to m1 v1I over m1 plus m2. If you plug it everything here, so m1 has 1000 kilogram, so v1I has 12 meter per second. You have to divide by m1 plus m2, 1000 plus 1200 kilogram. Okay. So, if you do that, I think you will get around 5.45 meter per second. So, if you look at the energy, energy is lost here. So, energy lost goes in the form of heat, sound and damage. That is why it is inelastic collision. This is not an elastic collision. Okay. In elastic collision, energy is also conserved, kinetic energy also conserved. Here momentum is conserved, but energy is not conserved here. Okay. So, we are focusing on the momentum. So, do not worry about the energy here, but if you look at the energy, energy is lost. So, in every collision momentum is conserved, the kinetic energy might not. Okay. So, in elastic collision both momentum and kinetic energy are conserved. So, the object bounce apart, but in elastic collision only momentum conserved and the kinetic energy lost to sound or deformation or heat, whatever, and object may stick together. Okay. So, billiard balls, can you talk about billiard balls? So, they are mostly elastic, right? Clay blobs basically totally inelastic. Okay. Clay blobs are totally inelastic. So, why conservation of momentum matters in real life? Okay. For example, you launch the rocket, okay, launching the rocket. So, expelling the gas backward, you expel the gas backward, that propel the rocket forward. Okay. In sports, tackles in football, rebounding in basketball, all momentum swaps, you know here. In particle physics, so collider rely on momentum to track invisible particles. In car crash forensics, like police use momentum to determine vehicle speeds. So, okay, from NASA to traffic court, momentum rules are all actually. Okay. The final question you need to understand here is actually where that conservation of momentum laws comes from. Actually, it's not comes from sky. It comes from the law, from one of the important law in the motion, third law of motion. Okay, Newton's third law of motion, which says every action has an equal and opposite reaction, right? If I push you on ice, you push me back just as hard. So, our momentum conserved, they cancel out. Okay. So, the deeper truth is even deeper. So, conservation of momentum comes from symmetry. Okay. I talk about the symmetry in physics. So, the idea that the laws of physics do not change from one place to another place. So, it is one of the most elegant connection in science. So, symmetry gives the conservation. Okay. So, let me recap the key idea here. So, actually the momentum is the mass and the velocity. So, in a closed system the total momentum always conserved. In elastic collision you have a kinetic energy also conserved, and in elastic collision object may stick and kinetic energy may be lost into heat, sound and the deformation. And the law is rooted in Newton's law and the symmetry of space. So momentum is like the currency of motion. Okay, so it never disappears, it only gets traded around. It's like a currency. Okay, so finally when you watch the soccer next time, okay, a soccer game, riding a bus, you always ask where is momentum being conserved. Okay, how does motion shift when people move, push or collide. Okay, so physics isn't about the equations, it is about seeing the hidden rules of this universe at play in skate park or starship